Hi everyone, my name is Sergey Muravyov. I'm a postdoctoral researcher in ITMO University, and today I'm going to present you the speech on automatic evaluation and tuning system for clustering algorithms. So here's the outline of our today's speech. First, we'll give some basic notations. After that, we'll speak about the quality measure selection for clustering tasks. So how can we choose the assessment technique for the clustering tasks? And then we'll consider the proposed method of selecting and tuning the parameters of heuristic clustering algorithms and evolutionary clustering algorithm with parameters tuned on the principle of meta learning. And finally, we'll talk about the implementation of all these things. So let's begin. Okay, so what is the clustering task? This is the task of dividing a given sample of objects into disjoint subsets or clusters, so that each cluster consists of similar objects, and the objects of different clusters differ significantly. This problem doesn't have generally accepted mathematical definition, but it occurs in many life domains. For example, in biology, in psychology, in image processing, and computer security, and also in many others. An important aspect of clustering problem is the measure of the quality of obtained partitions. There are two approaches nowadays how can we evaluate the resulting partitions. So the first approach is external measures that use third-party data about the problem being solved. For example, it can be already known partition or some benchmarks or some other things. And the second one is internal measures. So these are measures that use only the data about the structure of partition itself. It does not rely on any external data. So let's consider the classification of clustering algorithms. The first type is heuristic algorithms that build partitions based on some immutable heuristic. For example, these are k-means, dbScan, hierarchical algorithm, and many others. The second type is evolutionary algorithms that perform direct search in space of possible partitions in order to find the optimal one in terms of quality measure that is given as a parameter. Kleinberg formulated and proved the theorem on the impossibility of constructing a universal clustering algorithm. Therefore, it can be concluded that algorithms need to be tuned. An important property of machine learning algorithm in the context of their tuning is hyperparameter. In general, hyperparameters are parameters whose values are set before the start of training, do not change during the training, and do not depend on a given data set. So the slide shows an example demonstrating the importance of setting hyperparameters for a clustering task. So this is the example for dbScan. So the first example where we have one cluster, while it's evidence that we have two, and the second example with tuned hyperparameters, where we have already two clusters. That is correct. Today, many solutions for the problem of automatic selection and tuning of algorithms have been developed, but most of them are for supervised learning tasks. Most popular of them are implemented in the libraries like tpart, AutoScaLearn, AutoECA, and HyperOpt. For clustering task, only one solution has been developed, and this solution is based on meta learning. Its evident disadvantage is that the choice is made from a fixed number of algorithms. Okay, then we turn to the definition of meta learning. So broadly speaking, meta learning refers to a set of approaches, methods, and techniques aimed at transferring knowledge about solving some problems to accelerate the search for solutions to other problems. In a narrow sense, meta learning refers to the use of meta models, an approach for solving the problem of choosing algorithms in which machine learning algorithms are applied to metadata about the previous machine learning experiments conducted. Metadata or meta features describe the property of the assigned machine learning task. Here we will use a meta feature description defined by real scalar values. Also, it's important to note that in the concept of meta learning, the scope of the problem being solved is not important. Only the format of the presentation is important. Okay? As the part of formulation of meta learning problem in narrow sense, the characteristics of algorithms are predicted from the characteristics of the data. The objects in this task are data sets. In this way, meta classifiers are trained on the data sets of the data sets. Here we have gathered two such sets in which the data describe tasks from different line domains, including biology, economics, geology, and many others. An example of building such a data set of datasets for meta classification is shown at the bottom of the slide. Thus, the clustering problem doesn't have a mathematically correct definition. As a consequence, there is no universal measure of quality assessment. It's also impossible to build a universal clustering algorithm from the Kleinberg theorem. And the task of choosing and tuning the clustering algorithm is currently an expert one. So, the development of a system for automatic selection and assessment of clustering algorithms and their parameters is a relevant task for today. So, the goal of my work is to improve the quality of the solution to the clustering problem with specified restrictions on the time of its search. So, to achieve this goal, we have defined the following tasks. First, we have to develop an approach for automating the assessment of partition quality based on the visual perception by users based on the principle of meta learning. Second one, we have to develop a method for selecting and tuning hyperparameters of a heuristic clustering algorithm with respect to preselected quality measure based on the principle of reinforcement learning. The third one, we have to develop an evolutionary clustering algorithm with parameters that are tunable on the principles of meta learning with respect to a preselected quality measure. And after that, we develop a software package that implements the evolutionary algorithm and all the algorithms and methods mentioned above. And after that, we conduct the computational experiments to evaluate the performance of all the methods and approaches that we propose. Okay, so let's come to the first problem, to the problem of quality measure selection for the clustering tasks. So let's consider the problem of choosing a partition quality measure for clustering problems in more details. The most applicable methodology for creating a new measure of quality of a partition is to compare the results with the previously known partitions of the datasets based on their visual perception. So let's formalize this methodology. Let's introduce two criteria for visual perception. So the first one is evaluating the partition as adequate or inadequate, or the binary criterion. And the second one is comparison of partitions with each other for the purpose of ranking. So next, let's consider the problem of assessing the clustering quality based on the visual perception. We'll discuss our criteria in more details. An important aspect is the concept of assessor. So who is assessor? Assessor is a naive expert who does not have an expert qualifications in the fields of the clustering problem being solved. For him, the only thing important is the convenience of the data presentation. So each assessor assigns an integer score from -10 to 10 to the partition, from which we get an adequacy criterion corresponding to the sign of the assessment value, and the rank of the partition in weak order sorted by score values. The final clustering quality criteria based on the visual perception are aggregated criteria for adequacy ranking, adequacy and ranking for all the assessors. Next, we'll consider the task of assessing existing measures according to the proposed criteria of visual perception. Numerical quality measures also define the ranking of the partitions. Well, it's more or less evident fact. It's necessary to compare the ranking of the partitions given by measure and the visual criteria of the quality of the partitions. It is required that adequate partitions are estimated by measures higher than inadequate ones, and also that the rankings of the partitions set by measures and assessors are similar in some way. In the same way to the criteria for assessing the quality of clustering, we introduce the criterion of the measures adequacy. So it is the adequacy of the best as it is divided from the point of view of the majority of assessors. And the ranking criterion, which is the normalized distance between the orders of the partitions given by measures and assessors. So the formula is on the slide. So let's analyze the parameters of experiments to evaluate the quality measures. So what have we done? So the experiments were performed on the dataset of datasets 2D2000 that I mentioned before. That consists of 41 two-dimensional synthetic datasets and 159 multidimensional datasets from different line domains that were converted to two dimensions using a multidimensional scaling algorithm. So to construct partitions, we used 5 clustering algorithms with different fixed values of hyperparameters, and as a result, we got 14 partitions for each dataset, which were assessed by 5 assessors and 19 quality measures. So to assess the quality of a measure, we present 2 relations. So the first one is the ratio of the number of times when the measure met the adequacy criterion to the total number of experiments. And the second one is the ratio of the number of times a measure was the best in terms of the ranking criterion to the total number of experiments. Okay. So the results of the experiments are presented in the table, and from the results we can notice that not a single measure showed high results in terms of the proposed methods of assignment. Therefore, we can conclude that not a single measure considered to be universal according to the introduced criteria. In this regard, it is proposed to recommend the measure for each dataset. However, the recommendation of 19 measures is not rational, as it requires more datasets. In this regard, we chose 4 quality measures listed at the bottom of the slide in terms of their average rank scores across all datasets from the experiments. So these measures are silhouette, Glinsky-Harabas, one option of generalized Dunn measure, and OS index. Okay, so let us consider the problem of automatic recommendation of a measure for a dataset that is optimal according to the introduced criteria of visual perception. It is proposed to solve it on the basis of meta-learning. So we'll recommend the best measure using trained meta-classifier. In fact, the system of automatic selection of the partition quality measure acts as a new quality measure. So we named it meta-CVI. So what have we done? How we built the meta classifier. So the training set for the meta classifier was built on the dataset of datasets 2D200. The meta feature description consists of 19 statistical meta features described in the research made by Ferrari, and 90 landmarks proposed by myself that estimates the quality measures on all generated 14 configurations of algorithms, with help of which the petitions were obtained. So it was proposed to choose a random forest algorithm as the best meta classifier because it gave us the highest F measure. As for preliminary results devoted to the clustering quality measures recommendation, so we proposed the criteria for the quality of partitions based on the visual perception. Also, we proposed a method for assessing the quality measures of partitions based on the visual perception. And finally, a method of automatic recommendation of a quality measure for new dataset based on the visual perception criteria was proposed, which is also a new measure for assessing the partition quality itself that we call meta CVI. Okay. So earlier we considered the problem of assessing the quality of the clustering problem. Then we turned to the description of proposed method for choosing and tuning the hyperparameters of the heuristic clustering algorithm based on the reinforcement learning. So what do we have? So we have many algorithms. Each of them is associated with the corresponding space of hyperparameters. So for a fixed time t, we should find an algorithm that is optimal in terms of the value of a given measure of clustering quality. Let's split the time budget into equal intervals, then choose an iterative hyperparameter tuning algorithm. At the beginning of each interval or iteration, the method determines for which of the algorithms the hyperparameters will be tuned. In similar setting, such a problem is equivalent to the problem of multi-armed bandit, well, speaking about the reinforcement learning. The scheme of work of our approach is illustrated in the figure at the bottom of the slide. So here we can see different algorithms. So we have time budget split it into equal parts, and the agent chooses the priority for a certain algorithm at each iteration. And finally, we get the best result in terms of chosen quality measure. So let's consider the proposed method for selecting and tuning that we call MASCAH. It actually stands for multi-armed simultaneous selection of clustering algorithm with its hyperparameters. Such an awkward name. At each iteration, the agent selects one of the handles which corresponds to starting the hyperparameter tuning process for the corresponding clustering algorithm. At the end of the iteration, the agent receives a reward or some gain, which is the value of some function from a selected measure for evaluating the quality of partitions. So the scheme of these methods is illustrated above at the bottom of the slide. So let's move forward. An important part of the proposed method is the solution of the multi-armed bandit problem. That is the determination of the strategy for making decision on choice of the next handle. So how can we, what strategy should we apply to choose the next handle on each iteration? It is proposed to use so-called normalized softmax algorithm, which takes into account both the vector of rewards that we call R from all the handles at each iteration, and the vector of time corrections that we call U. Okay, so we carried out some experiments. Let's analyze the parameters. For the purposes of testing this approach, we gathered the dataset MD97 that consists of 4 synthetic datasets and 93 datasets describing real-world data analysis tasks from different areas of life. So 4 quality measures mentioned earlier were used for the assessment. We used also 7 heuristic clustering algorithms that are listed on the slide. And as the hyperparameter tuning algorithm, we choose SMAC algorithm, that is sequential model-based algorithm configuration. And as for the time budget was set equal to 1200 seconds for all the experiments. And the algorithm implementing the proposed method was compared as a percentage with the best heuristic algorithm with the default parameters on each dataset. So here the slide shows the hardware configuration. We'll omit its description in order to save our time. Okay, so the results of our experiments are on this slide. So part of the results on some data sets. So from the results of the experiments, we can conclude that the proposed solution based on the normalized softmax algorithm that we mentioned earlier works stable in most cases. So it's the most stable algorithm. So we have provided the comparison with regular softmax algorithm with upper condition bound approach, and we also provided the comparison with a random search and exhausted search, where we tune all the algorithms and their hyperparameters in parallel. As a result, we developed a new method to solve the problem of choosing a model of a heuristic clustering algorithm and tuning its hyperparameters based on the principle of reinforcement learning. Experiments that we carried out showed that the proposed normalized softmax algorithm works most stable and outperforms the algorithms that we selected for comparison that I mentioned on the previous slide. So we considered the problem of assessing the quality of clustering problem, the approach to its solution, as well as the method for selecting and tuning of heuristic clustering algorithm. Now let's consider the evolutionary clustering algorithm with parameters tuned using a meta-learning approach. Okay, so an important component of every evolutionary algorithm is the calculation of the fitness function. That is the quality measure, which is computationally quite expensive due to the nature of these functions. So let's consider that as a result of iteration, the object of the dataset has moved from one cluster to another. How can the measure of quality be calculated faster than recalculated it again from scratch? Since not for all the measures there is a possibility of a precise incremental recalculation in a time less than a full recalculation, we'll further use special surrogate fitness functions when it's impossible to do precisely. The idea is to maintain all possible distances between the dataset elements and centroids, so that it requires more space but it's fast in terms of time. So from the table at the bottom of the slide, it follows that the incremental recalculation for the measures considered is ahead of full recalculation in terms of computational complexity. We can also see that the complexity became linear. That's quite good improvement in comparison with full recalculation. So next, let's consider the suggested tuning method. In our work, we implemented 32 mutations, and after some experiments, we found out that the final quality of the resulting partitions is due only to the choice of mutations at each iteration, but not the strategies. So it was decided to use 1+1 strategy as the most efficient in terms of time. But an equally probable choice of 32 mutations on each iteration gives too large variance in terms of the partition quality. So to solve this problem, it was proposed to predict the suitable mutations for each data set. So we proposed to build a meta-classifier predicting a vector of mutations. To train the meta-classifier, we made several runs of 1+ lambda strategy on all configure pairs of quality measure and dataset, after which the distribution of usefulness of each mutation was constructed. So based on that, we built a binary vector of mutations recommended for use in each situation. So we should predict this vector for each dataset. So let's analyze the parameters of experiments. We used the dataset of datasets MD97 that we mentioned earlier. We also used same for measures of quality mentioned above. And for each configuration pair quality measure dataset, we performed 10 runs of the algorithm 1+1 with equiprobable choice from all 32 mutations, and the algorithm 1+1 with mutations from the meta-classifier. The comparison was carried out according to the average time and the average quality of the resulting partitions. Okay, so the results of the experiments are on the slide. So from the tables, it can be concluded the proposed automation method shows a better quality in 82% of cases and outstands in terms of time in 72% of cases. Also, we made a comparison with an algorithm based on the method of automatic selection and tuning of the heuristic clustering algorithm that we earlier mentioned. It's called Mascar. So we performed 10 runs of both algorithms on all the pairs quality measure dataset. The algorithms were compared using the normal distribution quantile. So the results of the comparison are presented in the table in the slide. So from the results of the experiments, it can be concluded that the proposed evolutionary algorithm is comparable with previously proposed method for selecting and tuning the heuristic clustering algorithm. Well, it might be not evident from the table. So we haven't carried out statistical experiments, statistical research to know it precisely, but still, at least they are comparable. Thus, we have developed a method for incremental recalculation of measures of quality of the partitions, an evolutionary clustering algorithm within automation of the selection of mutations based on the meta-learning. And also it was shown that the proposed method is comparable in terms of quality with the method for heuristic algorithms proposed in the previous section. Okay, so finally we move to the implementation. So the whole software package was implemented in Python. The link is on the slide. So let's describe it a little bit. CVI predictor actually makes a recommendation for each data set, which clustering measure should we choose. After that, it is fed to the either to reinforcement learning unit or to evolutionary clustering unit. So if it goes to reinforcement learning unit for heuristic clustering algorithms, we have the tuned algorithm as a result, and after that we apply it to the dataset and get the partition. In case of evolutionary clustering, we have the option of incremental measure calculation. After that, we perform the evolutionary clustering, and as a result, we get the partition directly. Okay. As for the recommendations for use, the software package can be used as an algorithm for solving the clustering problem for tabular data. The proposed method for automating clustering quality assessment can be used as a separate measure of quality that we have already mentioned. So we call it meta CVI. Also important to note, it's important to note that proposed methods can be used with other sets of clustering algorithms, other sets of hyperparameters, and another iterative hyperparameter tuning algorithm. So this is an important thing to get rid of the criticism. So we present here only the approach. So we have tested one configuration. So we have we have picked several clustering algorithms, the hyperparameter sets, and SMAC algorithm as a hyperparameter tuning algorithm. But still, you have an option to choose the other algorithms, and we state that our approach is still viable and it will work. And also, the proposed approach to assessing the quality of measures can be used for the arbitrary set of quality assessment measures. So instead of 19 CVIs, quality measures that we mentioned above, you can use your own set. The approach stays the same. Summing up, we can conclude that all the tasks stated in the beginning have been successfully completed, and the goal of our research has been achieved. In the end, so I'd like to present you the list of papers that were published recently on the topic of this research. So now it's around 6 papers. Actually, I'm planning to issue another one this year, and also I have registered computer program that is registered in Russian funds. Okay, so thank you for the attention. Feel free to ask your questions.